driven predictive control with persistence of excitation. During this presentation, I'll go through the motivation and the development. But I know it's been a long day, so in case I lose some of you during the presentation, the main message is that we were able to develop a pair of linear disjoint constraints that can maintain persistence of excitation during the control operation. So I'm pretty sure all of you have heard many times today already about the Williams fundamental lemma and persistence of excitation. So I won't go in much detail about this here. But the big idea is that it allows you to use data to represent the dynamics of the system in a non-parametric representation, using this structure here, and use best input and output data organized in the form of the Henkel matrix, whose columns are trajectories of length L of the system. And a key component or a key part of this is the sufficient condition that this input signal here, it must be persistently exciting of order L plus M. And what it means in this context to be persistently exciting, this Henkel matrix has full row rank, so it has linear independent rows. That would be important. So here we have a standard DDBC formulation. For those familiar with MPC, it's quite similar. You have your objective function. The first set of constraints correspond to the dynamics of the system. The second set of constraints are initial conditions. The third, a terminal equality constraint. And the last one is just a bound and input. An important thing to mention as well is, in this case, in this formulation here, this is a fixed data set. It can be updated as well. But results on this framework for nonlinear systems or time varied systems are available. And an important thing, indeed, if you use this formulation for these systems, is that the data must represent accurately the dynamics of the system. So if this is not the case, I've included an example here that I'll go back to it further later on in the presentation. Here I'm trying to track this set point for a system that is drifting, and I'm using some fixed data. And as you can see, the output drifts away because the data does not represent the system accurately. So what is one possible solution? That instead of using a fixed data set, you just keep updating the data that you use to represent the system with the most recent measurements. And this is done, in literature, people do this, but usually it's assumed that the persistent excitation condition is fulfilled. And what we want to work on, or what we did work on, is ensuring that this condition is fulfilled. So, as I mentioned, the idea that what we want to do is make sure that this condition is maintained at each time step. So we initiate, or we have the assumption that at the previous time step, this condition was fulfilled. So at time k minus 1, I have the input sequence that I'm using to represent the system, and I know it is persistently exciting. The question we're trying to answer is, how can I choose U of k so that the input sequence at the current time step is also persistently exciting? So this is the Henkel matrix that I showed earlier for the time k. I will introduce some notation because this block here, this one here, and this one here is just best data. So I just call them H11, H21, H12 to simplify. But this having linear independent rows can be equivalently describing as this system of equations here having z equals to 0 as its only solution. And from this definition, or from this equation, we can define the non-exciting input set as all of the choices of U of k for which there exists a z different from 0, such that this equation is fulfilled. This means all of the choices of U of k that cause persistence of excitation to be lost. And then, obviously, from this definition, what we want to do is to satisfy the exclusion constraint that the U of K is not in that set. From this definition of the non-excited input set, we derive this theorem explaining or characterizing this non-excited input set. There are two possible scenarios. The first one is that if these submatrix here, which is this bit here, if it has rank ML or it has linear independent rows, persistence of excitation is maintained for all choices of U, and then the non-excited input set is the null set. And this is, it's obvious. If these rows are already linear independent, you don't care much about what you do there. The more interesting case, or the second possible case, is that if this matrix here has rank ML-1, then the non-excited input set is given by this equation here, which is a hyperplane defined by this last bit of the matrix and by A and B, which are components of any non-trivial solution to this problem here. And you can use these components to characterize the non-excited input set. As I mentioned, the first case, not interesting. You can choose any U and persistence of excitation is maintained. The second one is the one that is more relevant in an application, because if you choose poorly, your input will lead to loss of excitation. One interesting thing to mention is that this equation for the non-excited input set defines a hyperplane of dimension m-1. So it's always one dimension less than the input. I've included an example two-dimensional here to show, but what happens always is, because the non-excited input set, which is this line here, has one dimension less than my input, it will bisect the hyperspace of the inputs and divide it into two disjoint possible constraints, possible input sets. And from this condition here, we can derive a pair of disjoint linear constraints on the input that guarantee that my input will be epsilon away from this non-excited input set. So if my input is either here or here, excitation is maintained, and obviously this epsilon is a tuning parameter that can be chosen. And the advantage of these constraints when compared to other constraints in the literature is that it fits nicely into the quadratic programming formulation of a predictive control problem, because its constraints are linear. So the quadratic programming problem remains a quadratic programming problem, whereas other PE constraints are non-linear, non-convex, and the problem, you'll have one optimal control problem, but a much harder one to solve. In this case, you solve two, but much easier problems to solve. I'll show the application of these constraints to a simple problem. I've included all the parameters here for reference, but an important thing to notice is this a linear system. I have this delta parameter that for one case is a fixed parameter, so it's a linear time invariant, and for another case it's a ramp, so it's a time invariant parameter. I'm trying to track this input and the output, and I have some constraints on the input. For the first case, as I mentioned, delta is fixed, so linear time invariant. These plots, they represent the average input and the average output for 50 in random initial sequences. And as expected, either the problem with no P constraints or a lower value of P or a higher value of P, they all track very well the reference output because the system is not changing, so the initial data is good, the updated data is good as well. I think the interesting thing in this case is when you analyze the condition number of the Henkel matrix, that as you increase epsilon here, you drop the condition number, so this leads to better numerical properties. But this case not so interesting. when you change for the linear time varying system with the parameter, the random parameter, it's as expected. The formulation without the P constraints diverges, because the original data that I had does not represent well the system, and the controller is not able to track that reference. But when I use the PE constraint here to update this data, you get a much better tracking. It still has some offset, but it keeps around the reference that I want to track. So to conclude the presentation, the main results from this paper is, one of them is the characterization of this non-excited input set, which is the set that I want to avoid, the set that leads to a loss of excitation. And then the second main result was the development of these constraints that can lead to two independent problems that you can solve in parallel and guarantee the excitation is maintained. And then I showed that by applying this to a problem, you can improve the performance of the controller. Thank you very much.
Yeah, thank you very much. Are there any questions? We have a bit of time.
In your first case, you said that where the upper part of the matrix has already full rank, you said that you can choose the view arbitrarily.
Yeah.
But might there not be a benefit of choosing it in a more sophisticated way to avoid that the matrix becomes or loses its rank later on?
Yeah. Well, what happens as well.
So to avoid the second case, the future.
Well, in these examples of these implementations, what I did is usually your the Henkel matrix is not squared; it's rectangular. So in many of the times, the first condition will be true because there are enough columns there. What I did for these implementations is that I just considered the last square bit of it. So I kind of force my controller to always update, and that would be the case, for example. If you just consider the less square bit of the matrix, you always have to update it. And then if you, at some point, you cannot use the constraint anymore, for example, because it's near a bound or something, you have some spare steps that you don't have to apply it, if that makes sense. I don't know if I answered your question. Yep.
Not sure.
We can talk about this. Yeah.
But here's the second question.
You have this parameter epsilon that defines the
Yes.
spread. Can you relate this to, for example, singular values, or is it clear that larger epsilon gives you better?
I've tried. There is a connection between this constraint and the matrix inequality constraint, but I couldn't find a direct connection between the rho that people have there and these epsilon. And one advantage of these epsilon constraints is that where is it? It's really easy to see how it fits into your input constraint side. You can easily see how much you're willing to give up on your input side and tune epsilon from that. When you use the rho, it's much harder to predict how it affects this. You can choose the same value and it will be a curve like this, or it will be like here, and you don't have a way to know in advance. So this is another advantage. This is much easier. But I've tried to make a connection, I couldn't find a way.
Yeah, thank you. I would have one question as well.